INCORE stands for the interdisciplinary, sometimes interconnected, but really interdisciplinary network community resilience modeling environment. And with that, Jong and I will be trading back and forth a little bit on this. And so the way we sort of think of INCORE is, wouldn't it be great to predict damage probabilities at an individual building level using physics-based models so we can transfer it anywhere? And then predict not just how many, but which households dislocate based on race, ethnicity, income, and other characteristics. And we do this by synthetically allocating them from the census block level into individual households. And then when we aggregate back up, that then reproduces the census. So, but then also to be able to predict changes in community level incomes by household demographic, changes in gross product, the tax base by sector as a result of the hazard occurring. And essentially, the ultimate goal is to make, or at least provide the information for people to make resilience-informed, socially equitable decisions. So we look at 5 areas. We really look at the first 4. We don't look at governance stability so much. And I think if you've been watching the news, you know why. And we look at population stability. And then here's just some examples of metrics within these 4 areas of community stability. So we look at population, economics, social services, as well as physical services. So one example, and this is just for the population, we're using empirically derived models. And this is, this started back in Hurricane Ike with Walt Peacock and others' work, and into our Lumberton study. And the reason it's complex is we can measure how many people remain. We'll be back in Lumberton actually in just a couple of weeks for our 6th wave or 6th year in a row. And to gather this type of data as well as other data. And so essentially the reason it's so complex is we know if they're still in their home, but if they leave, we don't know where they go. That's very difficult. So really out-migration and in-migration are extremely difficult. With population, one way we think of it is essentially as a 3-legged stool. If there's 3 legs remaining, then you can balance easily. If you take away one leg, it becomes a little more difficult. With only one leg, it's very difficult. And then if they're all gone, you're sitting on the floor. And so we think of that as work, school, and home. So resilience, I said I took away most of the resilience slides. This is at least one of them because INCORE really operates at this recovery level. And so we do model the hazard itself. We can put in mitigation alternatives, things like that. The hazard, the event itself, the drop in functionality, the drop in across the households as well as the businesses, and then into the economics model. And that's where we have this interdependent, interdisciplinary recovery that occurs in stages 3 through 5. John?
Yes. This is the INCORE, some component of INCOREs. As you know, we are dealing with a community, so there are components. We cover the physical infrastructure, including buildings and power network, transportation network, and water network. And on top of it, we do represent the economic structure of the community. We are going to cover a little bit about that, but we also CGE model to representing it. And then we have a social aspect through the demographic of the information and household and institution of the community. Next. So this is a kind of evolution of what kind of analysis you want to do with INCORE. INCORE stands for Interdependent Network Community Resilience Modeling Environment, which means that the scientists or researchers are able to model the community with interconnected component within the community. So first step, and the diagram shows, hopefully I can show the mouse here. So this is a damage and loss analysis we want to do when the earthquake or any disaster happens. The next step is we do a recovery analysis based on that interconnected network there. And then thirdly, based on the evaluation of the resiliency, we want to look at what is the alternative action to improve the resiliency of the community. That's what INCORE modeling environment wants to do. Next. So this is the diagram that entire center, we come together and come up with some idea that what kind of analysis or modeling effort we want to do. So I'm going to briefly go through that step. So you can see here the initial interdependent community description. It means that we define the community using some data and economic systems and social systems. After we define the community, next step is we did a damage analysis using the damage. The next step is the functionality of we are not just looking at the physical infrastructure, but also looking at economic impact on the social system too. So using all that information to compute that functionality. Obviously, next step is a recovery throughout the time. So you can see time is increasing throughout the loop that until the system is recovered fully. And then the 6A, looking at that, what is the status of the resiliency? It is a sufficient quality of the resilience we have, then we can stop there. But it's not, then we can go to 7A and 8A to looking at some of the policy changes or how we can improve all those resilience aspect of community. If that requires to have some changes of the infrastructure or social system, economic system, then we can go back to the initial 1A to go loop to identify what is a better policy for the community. Next. I'm going to give you a quick explanation about economic model and analysis. We are using a spatial dynamic computable general equilibrium model. What it does is basically it has the idea about how to represent economic sectors and government and also import and export of the community. And then this economic model able to come up with the equilibria of the system that we understand that what is economic status. Obviously, that equilibria could be impacted or changed based on some impact, which is this case is hazard that brings the damages in infrastructure that turn into some of the economic sector can be changed. Then we compute another equilibrium, then we'll have the differences between before earthquake or before hazard or after the hazard. So we know that what is economic impact of it. Some of the outputs here that have the loss in production, wages, and jobs, and also you're able to investigate those policy levels depending on what kind of level can impact on economic changes. Next. This slide shows the social science modeling we have. I think John briefly mentions about we are able to do some of the population and employee dislocation, but we are not just doing that as a census tract level, we are doing the household level. John mentions that we generate a synthetic population for each household based on census tract information, and we are able to understand each household, each building, how many people could be impacted by the hazard this case. And definitely we do the housing restoration and recovery. This case, we're looking at how the housing, the status changes when the disaster happens, what temporary housing and the long-term temporary housing, and then going back to permanent housing, or some people may leave the community too. So that's housing restoration recovery. And the business interruption restoration, looking at the business level of operation, how each business is able to sustain or come back to restoration efforts. And then those things that we combine with all the infrastructure analysis and damage analysis together. So it's all chained analysis. Next. Okay, John.
All right, thanks, John. So as I mentioned, the ability to start at census block level, which and then drill down, and so this just shows an example of how we can take a census block and then assign income, family level incomes to each structure or each household. So an example, this is, we'll get into a hurricane example later, but initially this is just an example that was fairly well developed. Many of you are familiar with the 2011 Joplin, Missouri event, just a massive EF5 twin vortex or multiple vortex tornado, deadliest, costliest tornado in history and deadliest since the invent of Doppler radar. And so what we do, and this should be, I believe it's similar to what you would do in your type of analysis, is we, in this case, developed a suite of 19 archetypes. These are used for hurricane, but there's the wind pressures and things were slightly different for that development. but they're also available. And so that's essentially the fragilities. This, again, for the engineers, this is sort of the methodology in that, and I can provide these slides rather than go through that. But so here we see the tornado scar. If we drill down, we can take a look. Here you see some strip malls, some residential buildings highlighted in whatever color, turquoise, whatever that is, cyan, I think. and then here's the Google Street image. So we can pull things out, and then we can assign the archetype and the resulting fragilities for that. And then here's showing that same image, but with the colors representing different archetypes. So then on the left, this is the city of Joplin. These are the different archetypes that were assigned by color. And then on the right, our housing inventory showing the number of people in different households that we'll be able to then deaggregate into the residential buildings. And of course, we can do that for businesses, other things. On the left, this is showing our interdependency between buildings and the electric power network. So the blue dots are just representing the 18 substations within Joplin, and then a cellular automata algorithm then enables us to tell which buildings are being provided power by a particular substation. And of course, that's dynamic and can change if the city has the ability to do that. Zhang had mentioned the computable general equilibrium model on the top right. This is what's called, it's a simplified version, but it's a social accounting matrix. And what that does is it defines with numbers, it defines all the differential equations that basically relate these to each other. And that's what the solver is solving to establish equilibrium after a disruption. And that disruption can be something positive too. It can be a new policy or something that's put in place, and then the CGE will solve it out to see what's changed in the economy. On the bottom right, this is just showing sort of the workflow or the algorithm flow that sets up and calculates population dislocation by logistic regression. And this comes from quite a bit of data over the years. So just to show you a quick idea of what can be done, can look at different retrofit strategies. So as simple as adjusting, the archetypes, and of course these are all solved out, and then we can say, okay, we can do that. We can look at if we were comparing 1 and 3, and we can look at the changes in the economy. So you can see employment on the left, domestic supply, residential and commercial, and then changes in household income by the 5 different levels. We can also look at and compare population dislocation as a function, and you can see you're reducing it quite a bit by going with retrofit strategy 3. Retrofit strategy 1, I should add, is simply status quo. So that's just what exists. So another thing that can be done to look at policies, as another example, is we can look at basically assigning, say, a community resilience goal. And so the example could be saying less than 0.5% in unemployment changes and less than 3% housing units dislocated after an EF3 tornado. And then we run through the example, random EF3 tornadoes. I think we have EF2 here for some reason, but we also did it for 2, 3, and 4 that you can see. And so you have different community goals. You set physical service metrics that you want to hit at the community level, population stability metrics, and economic stability metrics. And so we're saying, for example, we don't want more than a 0.5% change in domestic supply or reduction if we were to have an EF2 tornado anywhere in the city. And so we can look at this and we can go through and see what actually controls if these were our 3, say, resilience hazard planning levels: a routine, a design, and an extreme. Those don't correspond to civil engineering design or extreme, but the extreme may. And in doing this, what we show that the household dislocation metric controlled, and we would need to retrofit 34% of the residential structures. Now, interestingly, this whole analysis, the economics, everything, it's taking into account more than the residential structures, but the policy that we're investigating is just modifying residential structures. Yet it changes the other things because of the interdependencies across the disciplinary models or interdisciplinary models. Again, we can look at building recovery. We also have a household recovery algorithm I'm not going to go through, but and those have now been merged. It's not quite an NCORE, but it will be in about 2 months or maybe a month. And that is to look at when a building is actually available for someone to move in, rather than to have the household be ready to move in, but there's no building available. And so we've merged those two models. And so this is just showing, financial resources. This is specific to the state of Missouri. And so what we can do is we can look at different policies, things like relaxing building permit, the issuing of those. We can hire extra building inspectors. As long as it can be put in numerically, then we can solve it out, basically. And so what you see here is after a quarter, 2 quarters, and then after a year and a half, it looks like everything except the center of the path is coming back. And those were validated with data from Joplin that was recorded by video every 3 months or 6 months. So I want to jump to Lumberton, North Carolina. That was the study I mentioned. I think many of you are familiar with Hurricane Matthew came ashore and dumped a lot of rain. It wasn't such an impactful hurricane from a surge standpoint. This is a Jupyter notebook that you see on the right. So this is, if you were to use NCORE, this is essentially how you use it. You go through, develop a notebook, and John will talk a little more about that in a little bit. So I'll jump past. But and so from a hurricane standpoint, we have a combined wind wave surge model, but also inland flooding. And this is showing, that this is some of Omar Nofel, a former PhD student. He's at Florida International now on the faculty, but this is showing some of his dissertation work and others as well. And so a lot of statistics gathered, just a huge amount over the years. Of course, the different damage state levels. And then this is just showing for a single family house, this is showing the 37 damageable components that make up the fragility. So each of these has their own damage as well as cost fragility. And each, you can see, represents going into different damage states. And so those get combined in this fashion to develop essentially and here's just showing an example of 5, the decking, the foundation, the wood framing, and then they get combined. And of course, there's 37 of these that are being combined into the system level fragility. The same was done with an extensive surge going through different sites and coming up with loss estimates. And so there's a portfolio of 15 archetypes for flood. Of course, that was them being assigned. And then here's just an example of, say, damageable components for a very simple 1-story residential building. So these were, I just want to point out, these were used by the Office of Management and Budget earlier this year to look at, and they scaled them, but they were used in this white paper published in March to essentially look at climate loss projections due to flooding for all the U.S. government buildings in the country. And then I'll just click through these real fast. This is just showing some of the BIM archetypes. This is like a Walmart or something, a strip mall. And these are all office building, a school, health center, a church or a community center. And then this is just showing a mapping of the different archetypes in Lumberton. And then some of the policies or the actions that you can look at is we can look at things like installing a floodgate that you see here. This is just the validation on the left. We can look at changing the levee. We can add segments to the levee. We could look at different elevations as well, as you see. And then this shows just the impact, say A, nothing changed. And of course, D, C and D, very effective. And then adding retention systems, things like that. Those can be a little expensive if the natural terrain's not there. So there's a mapping algorithm for flood. This is actually mapping 500,000 buildings in Santa Clara County over in California. So, very well, most of the California counties are populous, but this one particularly. And then this is showing a flood in Santa Clara, and this is a simulated flood. This is not, and this is done outside of NCORE with HEC-RAS and then imported as a raster. And John will explain a little bit more about that. So, so one of the things that we did in the second 5 years, and I didn't talk a lot about this earlier, but going from this knowledge creation to an implementation phase within NCORE, and of course we're still putting in the science and the technology, and so we looked at the community resilience planning guide. They have a shorter version called the playbook, and these are the 6 steps. And so here you see the 6 steps on the bottom. And one of the things that we realized is that, or NIST also realized, is that a lot of communities were sort of guessing at what they thought the performance of different infrastructure and different sectors within their community would be before and after an event, because that was really the only way to do it. But NCORE, if the model's set up, NCORE can calculate that for these communities. And so we then integrated the playbook in NCORE. So we did this, an example is for Galveston County, Texas. And so this is showing, this is basically an analysis to get the wind, the wave, the surge, as well as the inundation duration. And this is coming from an AdCirc SWAN analysis that some of you may be familiar with. Again, we've got the archetype. So this is just showing an example of a few assigned. And then this is showing the real community on the left and our mapped community with the different archetypes and some scaling. And then this is just showing some of the type of damage analysis that we can do. Can also look at roadways and bridges. This is a recent paper that came out in a new journal called Resilient Cities and Structures. That's being led by Tongji University, but published by Elsevier. And then looking at dislocation from inaccessibility to different things. And so the ability to look at these types of interdependencies, things like that. And so, Zhong, do you want to jump through this, or I can if you want to? All right, I'll jump in. Okay, so this is basically a web app that we develop for each of our community partners. We have 4 partners. Galveston's one of them. So you can see we're defining the hazard for hurricane, and so this is driving. This isn't available like right now for anyone's use, but can be developed, and it's essentially driving the running NCORE on the servers at Illinois. So we can pick, we can say, okay, we're going to run Hurricane Ike. Here's our, the wave period direction, everything coming from AdCirc. And you can look at a 1%, a 100-year event, or we can look at a past event like Hurricane Ike in this case. And then here, so what we'll do is we'll view the results. This one was already run. This is just a video, so I don't mess it up. But and so we can look at building functionality with or without coupling with electric power. So we can look at the number of non-functional buildings in these clusters, the critical facilities, the housing that you see. These align with the NIST playbook, and so we can look at what's functional for different types of businesses and as well as different types of residential structures. We don't do emergency housing, and that's why that's blank, but that was just not part of necessarily the long-term resilience, but we could add that with the right mapping. Somebody can add that pretty easy. We can look at households dislocated, and so here we're looking by tenure, whether they're renters or owners. And then we can also switch that. We can then look at the households dislocated by other things, for example, race, ethnicity, or by household income. And then household typing, single versus multi. So for the economics model here, you see the total household income, and here we're just toggling between mainland and island. The community partner was interested in focusing on the island, but we did the whole county, and we can look at changes in domestic supply before and after the event, and again changes in employment, which of course we know is very important. All right, and Jung, I will pass to you.
Yes, from this slide and next slide, I'm going to get into a little technical about InCore's architecture and how the InCore works. We don't have actual demo, but hopefully this explains some of the underlying technology we have. So I'm going to start with the center part, InCore Web Services. So InCore is service-oriented architecture, which means that it has a web services, and then we do have some client interact with the web services. So first, we have many web services in InCore. The first one is a hazard service, which means user able to create predefined hazard. So for example, you can define some tornado or earthquake depending on your scenario, and you can use that unique ID of the hazard among your analysis. You can share with your colleagues and the researchers together. And DFR3 service contains situations, including fragility curve sets and recovery curves or damage functions and things like that. And it provides you that some equations, and then client understand how to parse the equation used in the analysis too. And it provides also some plotting service at the end that visualize those equations. And thirdly, data service. This is a data management service. You are able to hosting the input and output of the InCore data, and you can share and use for your analysis. So you could do that some access control over the data service that some people are able to access your data or not, you have a control. And space and user service is like that. So it is user management service. And then plotting service, I'll explain GeoV service. This is generating geospatial maps for your analysis outputs or your input data set or output data set. There's a variety of visualization you could do through that service. So this web service is able to access through the PyInCore, which is your right side. So we have the Python packages you interact with the web services. Especially PyInCore package, it contains several important parts. One is how to interact with the services. Second is actual implementation of analysis, like a building damage analysis or economic analysis you just saw, or social science analysis, all implemented within this PyInCore package. And then you will see that it interacts with services. And PyInCore Viz package contains visualization of those outputs. We find out some of the visualizations are specific to the outputs, so we have this package. And PyInCore data package contains a method and classes how to manipulate and generate some of the input data of InCore. One example is connect to the Census Bureau's API automatically, and it generates some input data for InCore from census data too. And this PyInCore package can be used on the left side. There's InCore Lab, which is online Jupyter Notebook system. So you can log in, you will have your Jupyter Notebook environment, and that environment already has the PyInCores are all installed, all necessary packages are installed. So you are able to use the online system to generate your Jupyter Notebook, start to do modeling and do analysis using InCore. And then right below at the yellow color box, InCore Web Tools. These are the web applications that you are able to search, browse, and download all this data available through the service. We know that sometimes web service is not easy to use. And then all the systems are implemented in a cloud computing system at NCSA. So everything is scaled automatically. So when we have a lot of users, that this cloud system scale and spun off all the servers to provide a better service for you. Next. And then this is a little summary. John asked me about this. I kind of think through, but some of them maybe is more applicable to users who know how to use a Python, but some of them is not. Some of the strength of InCore here. The first one we see that is in-core Python API is very consistent. In other words, if you know how to do building damage analysis using in-core and the Python, then it's very easy to do the bridge damage analysis, because syntax and how you plug in input, how to take the output is very similar pattern we have. So this also allows the chaining of analysis, that you could kind of chain different analysis if the input and output data sets are overlaps. Second part is in-core supports a popular data format, input and output. Especially we support the GIS data format, ESRI shapefile and GeoPackage, and CSV for the tabular data, and the raster for GeoTIFF data. So you could use that information, which means that the outputs generated from in-core, you could use that in ArcGIS or QGIS or Excel, any or packages you're used to using it, you can utilize output from in-core, then you can use in your application. Thirdly, in-core web service provides you with the latest data and information, which means we are keep maintaining this web service and database. And then whenever we release a new information, we send out an email to mailing list. So if you sign up in-core accounts, you'll receive the information of the latest data and information. And fourthly, in-core can integrate it or integrate other Python technology very easily. One example is, if you're familiar with OpenSeas, then we could combine that OpenSeas with in-core. And then there's a Winter, which is a water flow model originally developed by EPA. It's very easy to combine this two. I mean, this is very straightforward because it's all Python code. But one caveat is it may require to manipulate some data, because some of the data format is slightly different and things like that. So you may need that the data massage to make that this integration can happen. The fifth, Jupyter Notebook examples. All the Jupyter Notebook example available online. So you come to the in-core website, you can download the Jupyter Notebook and actually execute it. So you can very quickly learn how to use a Jupyter Notebook. Especially, we do have a Jupyter Notebook for test beds, John explains. So you will see what kind of actual research happened using in-core. Lastly, this is a comment also we got from our collaborator, is the in-core is open source, which means that you know how it runs, which means that some of the core algorithms and analysis is not a black box. So if you're familiar with some of this analysis, you will see that what kind of algorithm we implemented, what assumption we have in the models. Definitely we provide also publications related to the analysis, but if you want to, you can look at the actual source code to understand how it works too. Next. This is the in-core resources, in-core landing page you can visit. Especially, please go to the introduction page, that it will lead into how to sign up in-core accounts. It's free. It will give you to access to all the in-core web services and also Jupyter Notebook environment online. So you can try out right away. And then there's a GitHub link there if you're interested in source code and all the Python code that we are distributing through Conda packages. And if you have any question, you can send us the support email. We can respond to you right away. Next.
Yeah. All right. Thanks, Jung. So one thing I want to add to Jung, and I think this comes across to everybody, but for everyone is that so in-core is it's really, you can it's almost like because you're working in a Jupyter Notebook, it's really a computational environment. I think people refer to it as software, but it's really anything you can code. So if you don't like the population dislocation algorithm, I have a student that's working on her dissertation, and she's working on population outmigration as a result of climate change, and so they're doing their dissertation in core, using it almost like you would like a MATLAB or something like that, but it's because of all these technologies and these services that John was talking about that make it so much easier. You hit the ground running. You're not starting with a blank folder or whatever. So to conclude, I'll just say that resilience analysis, as you guys know, requires modeling before, during, and after the hazard, and the physical buildings, the network damage, no matter how comprehensive, and I think your project knows this well, is just a portion of the story. And so it's really that, to use that term that's becoming popular, the real digital twin, but we can't really see that part. It's the economics and the households. And then being able to comprehensively measure resilience in terms of stability areas is critical. And ultimately improving resilience through communication, decision, and actionable strategies is the goal. And so no matter how well we model the infrastructure, resilience is about the people, the equity, the safety, and working to improve the quality of life. And then finally, I'll just mention that we have 2 upcoming workshops. They're actually going to probably modify this. It'll be joint registration's not quite open, but this is part of the Inspire conference. And these will be free with hopefully some lunch in between the 12 and 1 slot you see there. And so this is a joint workshop within Core and Design Safe CI. And obviously we will acknowledge NIST and thank you for your attention. And thanks, John, for co-presenting.